Good afternoon. All right. Oh, this is crazy. All right, I'm gonna, one second. This is like a dream come true. Or no, yes, yesterday was the dream come true, and today is the wake up. All right, I'm gonna start. All right, I'm sorry, I'm 2 minutes late. Good afternoon, Andrew. Good afternoon, Vivian. Good afternoon, Jay Lynn. Good afternoon, we, she. I really probably should just say good afternoon, we, right? I've never asked you that. You should tell me. I don't know why I do that every time. But anyway, good afternoon, Mark and everyone. Good afternoon, Stephanie. Good afternoon, Catherine with an E. Good afternoon, Brenda with a Q. Good afternoon, Michaela. Oh, that's so nice to say. Good afternoon, Gabriella with a ya, and thank you for saying that. And good afternoon, Alyssa with a lowercase a today. That's unusual for Alyssa. Good afternoon, Lakshmi with a row. I'm going to bump on this again. Wait. Good afternoon, Celine. Thank you for saying so, Stephanie. Good afternoon, Stephanie. Okay, you are. Oh, okay, cool. Good afternoon, Guishi. Thank you for saying so. That's points for blowing in the circle. And hello and good afternoon, Josephine. Who I also think I still want correction on my pronunciation there. You know, the only thing more awkward than someone mispronouncing your name is then having them like talk about it a lot, probably, but oh, it is correct. Okay, cool. Okay, cool. Thank you. You know, there's also some before the days of Bitmojis and emoji and stuff, there's a huge difference in a text message between writing ha and ha. Have you ever noticed that? Like one seems so much more sarcastic than the other, but I don't know which one. But anyway, okay. Hello. Wait, hello. I want to look at the video for a second. I have to say, I'm going to waste more of everybody's. Cool. Okay. I am got to be really careful today not to waste your time or whatever, because it is correct. Okay. Oh, good afternoon, Warda. Good afternoon, Warda. Thank you for saying so. And good to get to know you. Wait, and actually, have I said hello to everybody? Wait, is that everybody? I think that is. Wait, did Charlie say hello? Wait, Charlie, what's the deal here? Wait, did Charlie? Your pleasure. Wait, I want to check. I'm totally, again, this is not attendance, but like, I'm going to be the first professor in history not to mark people off if they're not here, but to mark them off if they don't say hi. Like, how pathetic is that? Yeah, Charlie didn't say hi. What's up with that? After all, we had a whole lab together and he didn't even say hi. And my voice is going up. Welcome to my bar mitzvah. Okay, so what I want to say is physics stuff, but really, I did not. That was such a pleasure to see you all in lab. That really, for me, that was such a delight that I did not expect, and it was like crazier than I thought. And I also didn't realize it actually makes a difference to me now in this space. Like I don't know, I feel like we all just took a field trip together or something into a place called life. Yeah, no, and yes, the doodles were great, and they did last. I will say, because I ended up coming back. There was a lab after your lab. There was a 203 lab that I was visiting for a while, and definitely all the chat and the doodles survived at least through the 203 lab that went till 7 or something. I don't know if they're still there today, but yeah, no, I love that. Oh, and I'm totally kidding, Charlie. But wait, oh God, okay. Oh, multitask. Yeah. No, I was kidding, Charlie, but it's good to see you. And I will never mispronounce your last name again until I totally do. But yeah, good multitasking. I've heard about that. I figure I'm going to one day learn to multitask after I at least master single tasking, which I have not. But yes, Sarah, I'm so glad to have met you guys. It really makes a difference. Yeah. And hopefully I'll see you again in one capacity or another. But and I'm glad I'm getting to, yeah, anyway, it really is nice. So we do have to get back to physics. And also, let me say this too. Again, of course, there's no lab report or any like, there's no direct grade responsibility from is there a chance? Wait, sorry. Oh, that's very nice of you to ask. That's you, Lakshmi, thank you. So the most honest thing I can say about this, there's no, there is a chance I will see you again, because really I'm crazy. I had a whole dilemma about that last night. Believe me, I really started thinking like, oh my God, my life would be so much better on so many levels and easier if I would just do this. The fact is I teach somewhere else at that time. Oh, okay. At that time, I literally do teach something else at that time normally. And it's just that, they didn't have it yesterday. That's why I was able to do that. But so honestly, I can't, but I did have a major dilemma about that. And I like almost quit my other thing, which I totally cannot do. But I really started lamenting my other responsibility that I have at that time. And I will certainly tell you that I will, for selfish reasons, I will come back into that room. I will get a little sketchy with the other thing from time to time. But no, so there's a chance I'll be back again. And I'm saying this for I'm not saying that all of you necessarily would want that. And I think your arrangement will be good anyway. But yeah, I really enjoyed that. And also just, hopefully there's other ways that my paths will cross with some of you after all this. Again, on a slightly serious note, one thing that's even yesterday, even before I saw you guys, I did have the opportunity to meet at least one. I might have mentioned this. I met at least one person in the morning, who's not in your section, who took 204, I guess, last semester. I met somebody in the morning for whom I had written a recommendation. And in the recommendation, I raved explicitly about how well I knew that person despite like remote learning. And I meant every word of it. And then I even ended up showing the person the recommendation for weird reasons. And she felt very comfortable with it. But I had raved in the recommendation about how well I knew this person despite electronic relationship. And then I met her. And then like after, right, what I'm trying to say is, believe me, hopefully some of you will feel comfortable coming to me for recommendations when all of this is over. And I will be able to make a clear point about like, oh my God, they really made themselves known even under weird conditions. But now that I actually feel like I know you people somewhat, it'll be even better. And there's research opportunities and PRISM and things that I hope some of you stay in touch, or if you're going on in criminalistics or physics, or you come back for a master's, I hope our paths continue to cross. And I do mean that. And without getting too, I don't want to stay too cheesy for too long. We'll get to physics. But I also think you rocked that lab. Split. Oh, that's funny. Come on. SMH. Wait, what is SMH? Oh, somehow? Is SMH somehow? Am I like an idiot that I never knew? But yes, I'll split my chromosomes. But no, I will be back. And it was, and now let me say about content. That lab, which we kind of, you might have noticed, I mean, I sort of made up on the spot to try to address like where we were, and also to help some other things going on, like the other professor who was watching, so he would know what to do in his class, blah, blah, blah. We have a lot of new teachers that we're trying to coordinate. But you guys totally stepped up to that lab. Like you did that very, very efficiently and very successfully, honestly. And yes, it was, I mean, we've done a lot of labs like that in the past, but they don't usually go that smoothly as it did for you guys. And that's also given that none of us, you and me, none of us has been back in the lab, in the physics lab for so long. I'm quite impressed how you all just like stepped up to that, did it, got results. Even when some of you, when you needed corrections and I corrected them, and then you're like, oh yeah, got it, okay. Like that was like remarkably smooth. And that's not me, that is you guys. Because believe me, I have been teaching for a while. I've seen a lot of labs. They do not always go like that, even if I'm in the room. So that's on you. I mean, in a good way. So thank you. That also made me like want to do this more. Anyway, all right. So cheese, past the crackers. There's so much cheese. But yeah. Okay. So we should do some physics. I still owe you time. Now, also, please forgive. Now that you see, I'm as much of a maniac in real life as on the. And as you might have noticed, there is a lot of crazy. We're scrambling to. We just hired 4 new physics faculty members in the last week and a half because of all this COVID craziness. And we're still hiring more. So it's a little chaotic right now. I'm just saying that to say, please forgive. I have your game turn assignments. I have your thing on a spring. They're not being lost in the shuffle. They should have come back already and they didn't, but they will. I'm just a little bit trying to keep my head above water, but they will. Okay. So let's go to thing on a spring. But stop me. We're going to go back to thing on a spring now. We're going to go back to the homework 1 sheet. I believe, okay, correct me if I'm wrong. I believe we have gotten the answer to question 4 now. And now we're moving on to question 5. Finally, correct me if I'm wrong. I think I'm moving on to question 5. So actually, what I'm going to do for question 5 is kind of like what I did last week. I'm first, just so we can get some progress here or feel some concreteness. For question 5, in 1 second, I'm just going to write out a solution to it that I think is an adequate solution and show you the answer so you can check, if you think you did it right or whatever, and check your answer. Then I'm going to back up and actually explain the solution in larger terms for all of us. But I'm going to just give you the solution first so you can check. Okay, and stop me again if I'm wrong, but I think we're talking question 5 here, homework 1. Bear with me. Okay. I'm still looking at it. Right. I can't believe that. Right. Okay. Vivian, Andrew, Rishi, Gabriella, Mark. I'll know you forever now. Okay. Okay. I'm just changing it. I'm going to. Right. Excuse me. Oh. I'm so sorry. Hold on 1 second. This is another physics professor call. I'm sorry. Give me 1 second. sorry, that was Professor Walters. Just want to make sure she was okay. 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 I apologize again. Okay. This is a little bit of a mess. Again, I'm going to explain this in a minute, of course. And also, yours might not look exactly like this. There's various ways in which yours might look different from this. Really, there's more than one path to this answer. Partly, I'm just doing this again so we can be sort of concrete. And I would like you to copy this down. And please do copy this down. Whether you did it a different way or not, if you did it a different way, but you got the right answer, I think it's not a coincidence. I'll say this. So the right answer is 0.095 meters, like approximately. It's approximate because there's a square root involved. So maybe you'll get like 0.096 or something. But if you got like 0.113 or something like that, I would say that's wrong. Like that's not a rounding error. If your third, and again, not that I'm a big about significant digits, but just to give you perspective, there are some wrong answers to this that reflect wrong methods, reasonable but wrong methods. And that's sort of what I want to address here. So if your answer is like 0.096 or 0.093, then I think you're right. And even if your method looks different from mine, but seems to involve some of the same terms, then I don't think that's a coincidence, and I think you're fine. But I would still like you to copy down this method, and we're going to talk about it. If you did a different method and got a wrong answer, I think it's because your method's wrong. I mean, like, to be blunt. So I think you should copy this down either way. But of course, if you're looking at it and you're like, okay, fine, I believe you, but I have no idea what you're doing there, I certainly will explain in a moment. But I do think the answer is approximately 0.095 meters. I'm going to just give you a second to see if you can read my handwriting or whatnot. But then again, I'm going to talk about it. I think there's something in the chat. Okay. And sorry, I'm going to give you one more, or give me one more second. I'll give you one more second. Actually, I'm sorry. Yeah, give me what. It honestly, I would say too. You look at it for a minute and see if you make. Okay, great. Okay. Okay, I will start talking about it, but I think your job, like obviously you want to, if you did a different method and you got it right, then it's kind of your job to kind of look and see if you can make sense out of mine. But all right, I'm going to start. And you know what? I probably started one in step 3. I even probably skipped a step. I'm going to go to the next page. I'm going to tell you where that first step that I just wrote here came from. Really, I probably should have written first. And I'm even good. All right. So this is a funny way. I'm going to teach this in a funny way. I'm going to tell you what I just did there and sort of work backwards from what I did to what the larger concepts are. And they'll land in different places for different folks among you. Like, okay, so I'm going to flip back and forth between pages. What I'm saying is this first line here that I wrote, 1/2 kx squared plus 1/2 v and okay, no, actually, I'm sorry. Let me back all the way up. So the question of question 5 is given. The question of question 5 is at what position does this mass obtain an instantaneous speed of 3 meters per second, right? I mean, I believe that's the question. So where is it that the mass reaches an instantaneous speed of 3 meters per second? That's what we're solving for. That's the question. Note this. This really is the same question that's being asked in 4. It really is the same type of question that's being asked in 4, only in reverse and with the addition of one challenging detail. What I mean by reverse is question 4 was, what speed does the mass attain instantaneously at position x equals 0, right? So question 4 gave us a position and asked for a speed. And of course, that sounds really straightforward. That sounds like, oh, that sounds like a physics question. You name the spot. I mean, I name the spot and you name the speed. The thing that makes it a little tricky and that made us all of a sudden have to like introduce integrals and work and energy is that what we in question 3 wasn't the standard old physics 203 question of I name the time and you name the speed. Like really, that's what we spent a lot of time in physics 203 dealing with. I name the time and you name the instantaneous velocity or the instantaneous acceleration or something. And that was somewhat straightforward because time was the standard independent variable, and all these concepts like velocity or speed are all measured with respect to time. Like speed is like meters per second, right? Now we're asking a question that sounds equally simple, but actually takes it to a higher level. In question 3, we're saying, I'm not going to name the time. I'm going to name the position. And I want you to name the speed. And what the implication there is that things are happening as a function of position now. And that's funky dunky, because position we're used to position being the thing that depends on time. But now we're saying stuff is depending on position. Okay, so we had to introduce work and energy. So in question, so in question 4, we have this thing of I name the position, I want you to name the speed. And we all backed up and said, you know what, from here on in life, whenever that goes on, whenever there's a position speed relationship being asked for, let's think in terms of work and energy. That's what all of our discussion established in question 4, is that when you have a spot speed correspondence, then think in terms of work and energy. Okay, so now we get to question 5. Same thing is happening. It's a spot speed correspondence. We're just flipping it and saying, okay, we're going to name the speed. Can you tell us the spot? Right? So it's still totally a work energy question. We're naming the speed. We want you to name the spot. The only thing that makes it a little, right? So it's the same question. So we're going to deal with work and energy again, but I'm going to expand my horizon or expand my understanding of work and energy here. You might notice, like, it's still 1f(kx squared, 1f(mv squared), but I'm like writing it in a slightly different way now for a couple of reasons. For a couple of reasons. One reason is, now, even though it's the same question, just flipped, we're now getting rid of a certain luxury that we had in question 4. Question 4, we asked, what is the speed of the mass when it reaches position 0? There was like a built-in 0 there, that whether we knew it or not was kind of making our life easier, and kind of making our life easier. So much easier, we might not have even have noticed it, because we might not have noticed that there was a certain number that we had to worry about in the setup, because that number turned it to be 0. So we didn't even think about the number. Now we're saying, what is the spot where the speed is 3? And the spot is not going to be 0. We already established that at spot 0, the speed is 3.78. And the spot is also not going to be 0.15, because at 0.15, like meters from equilibrium, the instantaneous initial speed is 0. So we're looking for someplace in between the maximum position and the equilibrium position. We're looking for, right? Because we're naming a speed that's between 0 and 3.87. So we're looking for a spot that's between 0.15 and 0. So there's more numbers involved now. Now we're going to use the same method of energy, but the one theorem we got from last Monday, or, and maybe from an earlier part of your life, the one theorem that we got from last Monday is that work is the transfer of energy. When I do positive work on you, I give energy to you. In fact, very precisely and quantitatively. And again, this is a theorem. Hopefully I wrote it in a certain way last class, but if it's at all fuzzy to you, please write it again. Like work, or in English, work is the transfer of energy, specifically kinetic energy. Work is the transfer of energy, specifically meaning if I do 15 joules of positive work on you, then I literally give you 15 joules of what we call kinetic energy. What does that mean? It means you'll have 15 joules of kinetic energy more than you had before, and I will have 15 joules of kinetic energy less. I transfer the energy to you. That is the transaction known as work. And it is a statement, like it is a discovery, because work itself is like pushing you or pulling you through a distance. And we're saying when I push or pull you through a distance, I give you this commodity, this thing called energy. What is it? Well, mathematically, it's the square of your speed times half of your mass. What the heck is that? What that is your ability to do the same thing on someone else now. What is work? And you may want to write this down again. This sounds like a circle. If you think what I'm about to say sounds like a circle, you're getting it. But if you realize how it's ultimately a productive circle, then you really get it. Work is the transfer of energy energy is the ability to do work. Like literally, truly, like English, work is the transfer of energy. Oh, okay, that's cool. So what's energy? Energy is the ability to do work. Now, if you think that sounds like a circle, you are definitely listening to me. Like it does say, right. Okay. And that's where I'm going with this. That's awesome, Weishi. That is where I'm going to the level of conservation in a minute. Yes, right now, she's totally right. She's totally right. And I'm going to get there in like 1 second. What I'm saying right now is just that what work is a passing of energy from one system to another. What energy is the ability to make that pass. Right. And that means the two are tied. One is like the verb and the other is like the noun or whatever. Again, and I totally want to address the we, she thing. Before I do though, just note that in a way that is like that's like a weird closed system, but it is just like money. Money is the ability to spend money, right? Now, because money comes in different forms, it actually ultimately like somehow we give a crap. Like, why do I want to be rich? I don't know. I don't even think. No, why do I want to be rich? Because then I would have a lot of money. Why do I want a lot of money? So that I have the power to spend it, which means get rid of it. Well, what does that really mean? It really means exchange it for something else of another form that I happen to want more at that moment. And same thing. And now this is where we get to the we, she point. Like work is the transfer of energy. Energy is the ability to do work. First of all, if any one given system has no work being done on it, then it's neither gaining nor losing energy. So any one system that doesn't have work being done, net work being done on it, conserves energy. If you know for a fact that no net external work is being done on a system, if you know for a fact that no net external work, like no work is coming from the outside of a system, from some other system, doing work on that system, then you know for a fact that that system will conserve energy. Well, there is certainly one system I know is never having any net external work done on it. One system I know never has any net external work done on it. That system is called the universe. Why? Because net external work means work done from the outside. And by definition, nothing is outside the universe. Because if we found something outside the universe, we'd redefine the universe to include that thing, right? The universe means every freaking thing. So nothing is being done from the outside onto everything. Therefore, within the universe, the total amount of energy is not changing. That's implication one of what she said. That's right. I mean, it sounds like a dumb point, but everything in physics sounds like a dumb point once you break it all the way down. In the universe, the total amount of energy is conserved because nothing is happening to the universe from the outside of the universe. But also on Wishi's point, I mean, I don't want to say a lot about Wishi's point. Second of all, actually, I want to think how deep do I want to go on this? Hold on a second. Let me just think for a second. I'm sorry. Yeah, actually, look. Oh, wait, chat. Something in the chat. Oh, so yeah, okay. Well, I'm really glad she said that actually. So if you go to this next page, where I'm sort of expanding on what I said over there, I'm going to ultimately say yes, for any system that the total amount, for any system that is not having any net external work done on it, its total mechanical energy should not change at all. And that's called conservation of energy. It's basically just saying net work equals transfer of energy. When the work is zero, then the transfer of energy is zero. I'm now going to go a step further and say, okay, if we define something called the total mechanical energy, now I have to expand on that in a moment. But if I define something called the total mechanical energy, I can even start using Wishi's observation in a very specific problem-solving, helpful kind of way. Like, not only is it true that a system on which no work is done conserves energy, but in fact, if I start looking at certain systems certain ways, I could even say that in a system of some that has moving parts, that has objects moving around, I could even, if I'm careful and define things in a certain way, I could say, the total amount of, in a conservative system, a system that's conserving energy, I could even go so far as to say the total amount of energy at any one spot, at any one location, or the total amount of energy when the system is at a certain location is the same as the total amount of energy at every single other location. Like, remember in the first place, work is force through displacement. Work is the accumulated effect of force acting from one position to another. The whole reason that we're looking at work and energy in the first place is because we're concerned with situations where force acts variably from one position in space to another. Work and energy is all about the relation of force and velocity and acceleration to position in space, point in space, as opposed to point in time. So I want to take this conservation of energy thing really seriously. I'm going to say, so now I'm going to say that for any conservative system, that conserves energy, that means not only is the total amount of energy the same, but in fact, the total amount of energy will be the same from position to position. Like, that's a more detailed claim to make, as long as I define total mechanical energy in a very specific way that I'm about to in a moment. Okay, so I'm expanding here. I'm trying to build up where I got my first statement in that algebra from. So here we go. Okay, just to be as clear as I can be, what I'm still, like, I gave you the answer for question 5, but I'm still talking through question 5 now. I'm trying to explain really where I got the answer from. Secretly, I'm using this whole sheet as an excuse to teach all these physics topics that we need for the rest of the semester. Okay, so secretly what's going on, what's about to happen right now is I'm about to use question 5 to give you my perspective on potential energy and kinetic energy. I know many of you have seen it before in many other classes, but I want to show you how I think of them, or how we use it in this level of physics. Okay, so I'm introducing now, I'm about to introduce, like, my idea of conservation of energy, like she said, how it relates to potential energy, all that stuff. I'm doing this all in the context of question 5. Again, this is for teaching purposes. I'm not saying that you'd have to write out all of this. If you were handing in the homework, you would write out more or less what I just did on the other page, okay? But now I'm asking those of you who've never heard of potential energy before, or never heard of conservative forces before, or conservative, then please follow along for sure. Those of you who have heard it, please trust me or have faith that it will benefit you to hear it this way, or hopefully this will be able to find out whether you'll be able to do a check on your own understanding. But again, even if you use these ideas to do your homework, please try to absorb them in this way. And it shouldn't, if you've already thought about them, then hopefully it won't hurt too much to put them in your brain this way. So I'm saying this, and some of what I'm going to say, I almost guarantee will be new to everybody. If nothing else, there's some pieces of mathematical notation that I have to give you here that may be new to everybody. So I'm going to start with this. Again, this is me teaching now in the context of question 5, showing you where I got the answer. You don't have, okay, you get it. So okay, first I want to say in English, well, if I'm reading my handwriting, I'm saying, now here's an observation. And again, to all of you, like this making an observation here. You may or may not have noticed in your life, in your physics life thus far, that some forces, when they act on a closed path, or what you might call a round trip, a one-dimensional round trip, some forces, when you ask them to act in a certain direction and then come back and act in the opposite direction, some forces, when you ask them to do a bunch of work out and then come back into where they started. So from now on, I'm going to call that either I'm going to call that a round trip, but it's not really round. It's like there and back, right? So the technical term for that in physics would be a closed path, a path that closes back in on itself. Some forces, when they act along a closed path, do a net work of 0. Other forces don't. And I mean, like, necessarily by definition of those forces, like we would know in advance whether they would or not. Let me give you a quick example. Like friction, okay? If I were not a total spaz, okay, that's a song. If I were to push this object out, slide this stylus out along my rough hand toward you, right? So I'm pushing the stylus toward you along my hand. While that's happening, friction is exerting a force on the stylus, like in the opposing direction. It's like friction is slowing down this. No tricks up my sleeve, just what you would think. Like friction is like slowing down the stylus, like robbing it of kinetic energy as it goes, making it slower than it otherwise would be, right? So while the stylus is moving toward you, let's call that the positive direction, friction is acting against the stylus in, let's say, the negative direction. So the work being done, force times distance, the force is in one direction, the displacement is in the other. So it's like negative times a positive. The work being done by friction is negative. On the way out, on the path toward you, the work being done by friction on the stylus is negative work. That's not supposed to be a surprise. That's not like a big thing, but it also makes sense though, right? Like friction's doing negative work. That means it's not giving kinetic energy to the stylus. It's taking away kinetic energy from the stylus. Like it all adds up. I think you would agree, right? And feel free to say so in the chat or not or whatever. But okay, so on the way out, friction does some amount of negative work. If the friction force is 13 newtons and the displacement is 2 meters, then the work done by friction is like negative 26 joules, example, right? But now, and by the way, while that's happening, my hand might be doing some work as well. and maybe if this whole thing is constant velocity, maybe my hand's doing the exact same amount of work. I don't care, like, and that's fine. That doesn't contradict anything. But I'm just right now, I'm just examining the force of friction to make an observation about it. Right? Okay. So on the way out, the stylus friction's doing negative work on the stylus, taking away kinetic energy. Then the stylus starts coming back in. Okay, because I'm pulling it in with my hands, not because of any tricks or weirdness, but the stylus starts coming back in now. So I'm still tracking what friction's doing. And let's say the stylus comes back all the way back to where it started. Well, on the way back now, the stylus is now moving in the negative direction, is now just being displaced in the negative direction. Friction is going the other way now. Like it's still going against it, but it's now pointing in the direction that our coordinate system calls positive. Right? So they're still in conflict, the displacement and the friction, like that's what friction always does. So even on the way back, the work done by friction is negative, right? Again, this is not meant to be a trick or a surprise. I'm bringing it up as a point of contrast. On the way out, the displacement of 2 meters, friction does negative 26 joules of work, arbitrary example. Then on the way back, for those full 2 meters, assuming friction's still the same friction, on the way back, friction's going to do another negative 26 joules of work. So for the entire round trip, friction does a whole bunch of negative work. In this case, negative 52 joules of work, right? Again, arbitrary numbers, but I'm just trying to make the point that over a round trip, a force like friction does net work of non-zero amounts. Happens to be negative in the case of friction. Then if you look at that whole example, you could look similarly at what my hand, the hand that was moving the stylus, you could look at what my hand was doing, or you could imagine there was a string pulling the stylus, and the entire argument I just made could be made for that string pulling the stylus as well, the tension in the string. Only there it would be a positive, like the string pulls the stylus out, the string is pulling out, the stylus is going out. So it's positive work. Then the stylus starts coming back in because the string is pulling in. So on the way out, it's like a positive times a positive. On the way in, it's like a negative times a negative. Either way, a string pulling the stylus would do a total net amount of work of positive 52 joules, right? Again, if you get what I'm saying, good. And if you're thinking like, why is that? Like, yeah, that's obvious. Fine. But now, so that would all be demonstrating the idea that something like friction, something like tension in a string, something like the normal force from my hand, if I were pushing, all of those forces we would call non-conservative. They don't conserve, back to Rishi's point, because over a round trip, they do a net amount of work. Therefore, they give a net amount of energy, or they take away a net amount of energy over a round trip. And why am I even caring about round trips? Because round trip means a trip where you end where you start, where you end at the same position as where you start. So non-conservative forces, if you think about it, like even if you undergo some phenomenon, even if your position, even if your net displacement for the whole thing was zero, even if you end up where you started, still somehow you gain or lose energy from these forces. So these forces do non-conservative work on you. They like do something to you that ends up with a different amount of energy from where you started, even though you end up at the same position. They're non-conservative. Now, I would say they're the norm. I'm not saying they're interesting. They're like the norm. But then, in contrast, you have forces like gravity, where, try to say this more quickly, where with gravity, if I could bring a pen up and then bring it down, or even better, I could just throw a pen up and then it comes down, which already is interesting because I can't do that like on a surface. I can't like throw something on a surface and expect it to come back. But with gravity, I could throw something up and let it come down. And if I look at what gravity is doing through that round trip, say I throw it up to a height h and then it comes down back to the ground. Well, on the way up, the stylus is displacing up, call that positive, to a height h, while gravity, mg, pulls down. So on the way up, the work being done by gravity, the work is a negative force times a positive displacement. Negative times a positive makes a negative. On the way up, gravity is doing negative mgh work. Where did I get mgh? Well, the force is mg. the displacement is h. So the force is negative mg, the displacement is h, so the work is negative mgh on the way up. That's the work that gravity does on the up. That's the work that gravity does on some m if it's flying up to a height h. Then the m starts to come down. Now it's coming down, it's displacing down negatively, you could say. The force of gravity is now still pointing down. This is a subtle distinction that, again, it's obvious if you just think about gravity. Everybody knows gravity is always pulling down. And the friction point was obvious if you just, everybody knows friction flips its direction to oppose your velocity. But think of them in contrast to each other. It's a very sharp contrast. During a round trip, friction will flip its direction to always be opposing your velocity. But during a round trip under gravity, gravity doesn't flip its direction. It's always pointing down. Therefore, on the way up, gravity is doing negative mgh work. On the way down, gravity is doing positive mgh work. So the net work done by gravity throughout the entire round trip is zero, right? I mean, it's plus mgh plus minus mgh, zero. Because gravity is always pulling you down. Gravity has this, right? So gravity we would call a conservative force. But the reason specifically we call it a conservative force is because it does zero net work around a round trip. Now, I might even have had a hint that it was going to do, like, why? Because it's always pulling down. So even before I did the round trip, I might look at me like, gravity's always pulling down. Like, it always wants everything to be on the ground. The ground is kind of like an equilibrium position. Like, gravity's always wanting stuff to be there. Kind of like springs. Springs have equilibrium positions. Like if you pull the spring out, it still wants to fly back to equilibrium. And springs, like gravity, like the force of a spring is negative kx. When I'm pulling the spring out, when I'm pulling the mass at the edge of the spring out, while the mass is being displaced positively, the spring is pulling negatively. The spring is doing negative work on the mass as it goes out. But then when I let it go and the mass is getting slower and slower, like just like when something goes up, gravity's doing negative work. I should have said a minute ago, just to be clear, like when something's flying up and I'm saying gravity's doing negative work on it, that makes sense. I think it shouldn't actually be a shock because as the thing is going up, it's losing kinetic energy. It's getting slower and slower. Then it starts coming down. Gravity's doing positive work on it. It's gaining kinetic energy, getting faster and faster. All right, same thing with the spring. If the spring's going out, it's getting slower and slower. Then when I let it go, or then when it's let go and it starts coming in, now it's displacing negatively and the spring is pulling it negatively. Negative times negative is positive. Like the force and the direction and the displacement are in the same direction. So on the way in, the spring does positive work. So on the way out, it's like negative 1/2 kx squared. On the way in, it's positive 1/2 kx squared. Ultimately, I say then that gravity and spring both have this special property where they do zero amount of work around a round trip. I'm going to call them conservative forces from now on. Then I'm going to notate this mathematically. I'm going to say from now on, Okay. So now here's the point where, again, I'm sure there's many people in the room who like, I mean, I hope that are getting what I'm saying. And maybe even people in the room are like, yeah, I've always gotten that. Like, that's not news, yeah, about. One thing I'm adding now to the news is I want to put it in this mathematical form. I want to give you a piece of mathematical notation that I think many of you maybe have not seen before. You know, there's indefinite integrals and definite integrals. Definite integrals are evaluated from one limit to another, not limit in the crazy, hard sense, just limit as an endpoint, right? Like a definite integral with the definite integral of f dx would be evaluated from like x1 to x2, or often in our cases from like x equals 0 to x equals x naught or something like that, right? Well, the definite integrals are evaluated from one limit, from one endpoint, one boundary to another. Here's something called a closed integral. And in particular, in the case of our context of one-dimensional integrals, this is technically called a closed path integral. A closed integral is this is me. Now, I'm not assuming you know this. I'm telling you for future time in our course. If you ever see an integral with a circle around it like that, it means it's a closed integral. That means it's a definite integral, but instead of being evaluated from like A to B, it's being evaluated from A to A. Or instead of being evaluated from X1 to X2, it's being evaluated from X1 back to X1. It's literally what it sounds like. It's if you integrate along a path that brings you back to the start, we call that a closed integral. And it's definite, it has an answer. It's like a doable thing in math. And what I'm saying right now is any force for which when you integrate it along a closed path, any force for which when you calculate the work, when you integrate that force from somewhere to somewhere else and back to the original somewhere, if you get 0 for that total, then from here on in, we're going to call that force FC a conservative force. A conservative force is that, okay? Two examples we have so far are mg and kx, the gravity force and the spring force. In fact, to be clear, those are the only forces we have so far in this class or in our class that are called conservative so far. The only ones we have so far are gravity and spring. Any other force that ever comes up in our class so far is non-conservative. I'm just going to note that. Notice side. So gravity and elasticity are going to be known as conservative forces from now on. And note, not by coincidence, both gravity and elasticity, spring force, seem to have an equilibrium orientation associated with them. Like when we think of gravity, we think of things wanting to be on the ground. When we think of springs, we think of things wanting to be in a certain spot. They're always bringing something somewhere. Not coincidentally, that ends up meaning that if you go away from that thing and you come back, the total net work done is 0. Forces that are conservative generally have some sort of equilibrium position or orientation associated with them. Okay, now where am I going with all this? What does that have to do with anything? And I realize there's only 14 minutes left. Where I'm going with this is, well, I'll tell you. Oops, sorry. Okay. What I'm saying, I'm here. I'm trying to give you my definition or my understanding or my introduction to the concept of potential energy. I know many of you have heard of it and used it in many, many classes in your life, maybe even starting in 6th grade in cases of some of you. I just want to alert you again, just like last week when I introduced kinetic energy. Of course, I know that you all know about kinetic energy, but the little algebra that I did, or not last week, 2 days ago, the little algebra that I did wasn't trying to say, oh, look, we have something here that is now related to our old concept of kinetic energy. What I was trying to say in the algebra on Monday is, here's where kinetic energy as an idea comes from. I was showing where it gets introduced in physics and why. Now, similarly here, even though I know as a human being that you've heard of potential energy before, as a physicist right now, I am not assuming that we've ever mentioned potential energy before. It's like I'm about to discover it or invent it for myself right here on this page. And I ask you to sort of try, be in blank slate mode for a minute, forget anything you know about potential energy for a minute. Here's where it comes from in physics, as far as I'm concerned. So top line is FDX equals delta KE. We say that when we do work on something, we transfer kinetic energy. The work I do on a system gives kinetic energy to that system, right? That's what we say in the top line. And that's a theorem, not a definition. It's just it's a theorem. Then, oh, excuse me, wait, there's one thing, let's put a C here. Okay. There should be a C. Yeah, do you see the C? I'm now on the, sorry. I'm now in the middle equation in the sheet. We now say, in fact, that should be a definition. We now say that there are certain forces called conservative forces, such as the spring force or the gravitational force, that when they do work out and back, the total amount of work that they do is 0. So what that allows us, so that means if we know that certain forces are always going to give you, in the end, are going to conserve energy. If for certain forces, we know that if the force brings you away, but then brings you back, that for the total thing, your energy won't be changed at all. Then it gives us this weird ability, this predictive power, this computational advantage to say, oh, I got it. As long as we're just looking at a conservative force, let's talk about gravity for a second. Since we know what gravity is going to do for a whole round trip, anytime gravity is acting on some one leg of a trip, if something's just going out, so if something is being raised up, I know that when I raise something up to a height of h, that gravity is going to do negative mgh. Sorry, I know that to raise something up to a height h, I've got to do, gravity is going to do negative mgh work on the thing as it's going up. So in order for me to raise this pen up to h, I've got to match gravity. I've got to do positive work mgh on this thing. So I'm doing positive work mgh. I'm giving it kinetic energy. Okay. And I bring it to the top. Now I did all this positive work. I gave it all this kinetic energy. But now the thing is stopped. But then I suck it at, now I slow it down and I stop. And now the thing's sitting here at height h. I did all this work. I gave it all this kinetic energy, but now it's sitting here. So it doesn't have any kinetic energy anymore, right? And all the work I just did seems to have been wasted or accounted, or I'm not remembering it anymore or whatever. And that would be the end of the story, except I know for a fact that if this pen ever comes back down to where it came from, if I release it and I let gravity bring it back down, I already know in advance how much work gravity is going to do to bring the pen back down. I know that I know that this big trip that I just underwent could be viewed as the first leg of a round trip. I know that for the second leg, the back leg of that round trip, gravity is going to give back exactly what was lost on the way up. So while this pen is sitting here with no energy whatsoever, I can actually already predict how much energy the pen will have if it ever lands back down again. I already know how much work gravity is going to do on the way back down because it's just the negative of whatever I did on the way back up. So I can say, while this pen is sitting here, because the only force involved is a conservative force known as gravity, while the pen is sitting here with no kinetic energy whatsoever, I can say that it's storing energy. How much? mgh, that it's storing energy, and I can call that potential energy. And I can save myself a lot of computation and a lot of experiments and just right away predict correctly that while this pen is sitting here, while this pen is sitting here, not by virtue of its motion, but just by virtue of its position, it's storing energy, mgh, that I'm going to call potential from here on in. How do I know? Where did I get mgh from? What is the potential? If you look at the bottom integral, I'm saying that the gain in potential energy that it has here, like it had no potential energy down here, it had 0. But the amount of potential energy it gained to get here is simply a calculation of how much work I had to do to get to there, how much work I had to do against the conservative force, or even better, if you look at the integral, it's just a prediction of how much work the conservative force will do on this object to bring it from this spot, x naught, back to 0, back to equilibrium. The amount of work that the conservative force will do to bring an object back to equilibrium is known in advance for conservative forces, because it's simply the same as how much work you had to do to bring it there in the first place. So from now on, we can say that the work that a conservative force would do to bring something back to equilibrium is from now on called the gain in potential energy. It's the energy that's being stored in advance before that work actually gets done. Where is the energy being stored? You might say it's being stored in the pen. You might say it's being stored in the earth. You might say it's being stored in the earth pen system. But I'll tell you what I say. I say where that energy is being stored is in our mind. It's in our memory or in our advanced predictive powers. In other words, it's in a way, it's a computational technique or a construct or an idea that we came up with because we can have this convenience of thinking about energy being stored in all and only the cases of conservative forces. Bottom line, potential energy is the work that would be done by a conservative force to restore something to equilibrium. And once we invent that idea, and I know we have 4 minutes, then I say, hold on a second, get tons of messages. Sorry. Sorry. What I'm saying right now is, in the last 3 minutes, is that from now on we can define Okay, I'm going to stop right here. This brings it full circle now. I'm saying that if you go back the other, I'm going to leave it here for a second, or we can turn it back a page if you need. But I'm saying from now on, a theorem from that. So I'm saying, what is potential energy? But don't memorize that potential energy is mgh, or potential energy is 1f(kx squared or something like that. I'm saying in general, potential energy is the work done by a conservative force to restore a system to equilibrium. There's no such thing as potential energy associated with friction. Like friction does not store energy. Tension does not store energy, blah, 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 blah. But springs do, and gravity does. So the potential energy due to a spring is the work that a spring does to bring you to equilibrium, i.e. 1f(kx squared). So from here on in, the total amount of energy you have, if you're a conservative system, any kinetic energy you're losing, we're saying from now on that you're storing as potential energy. And when you gain kinetic energy, we're saying you're giving up that stored energy. Again, we're just saying that, like, because we can, because we know, because what we're doing is deliberately viewing any work done by a conservative force as one leg of a full round trip. And we're just predicting what's going to happen on the backward leg of that round trip. So from here on in, it's a theorem to say, to bring it back to Weishi's thing, and we're going to shut down, and I'm sorry, like tons of things are happening. We're going to shut down in a second, but to bring it back to Weishi's thing, I'm saying our version of conservation of energy is from now on for a conservative system, that is for a system on which no non-conservative forces are doing work, the total amount of kinetic plus potential energy at any one spot, any one position, is the same as the total amount of kinetic plus potential energy at any one spot. So that's what I set up for question 5. And then I just plugged in the values, basically. What were my two spots? My two spots were where v equals 3, because that's what I was looking for. I was looking for that x where v equals 3, and I didn't know it. I was solving for x. And the other spot I chose was some spot where I knew the v. I happened to choose the other spot where v equals 0. So that spot was x equals 0.15. I could have, you could have, and you might have chosen instead to compare to the equilibrium, because at the equilibrium, we also know the v. It was 3.87. So you might have, but in one way or another, if you do this problem, you have to compare a spot that you're looking for the spot that you're looking for to a spot that you know something about. What's something? The v. Okay, I'm going to end there. Sorry, I have to actually go to a meeting right now, so I'm going to shut down if that's okay. But I'm done. If you're good, I'm good. But thank you very much. Thank you. All right, and we'll see you next week. Yes, take care. Thank you.
Have a great day, Professor.
Thank you. Good to see you. Thank you.